In this video, we'll talk about how special techniques fit into the whole process of deciding how to solve an integration problem. So when I say special techniques here, I mean basically trig substitution, trig integrals, and partial fractions. And why they fall into these special techniques category is the fact that they have very specific uses and they show up in very specific places in problems. It's not usually hard to see when this technique is going to be used, and it has a certain method to solve it once you get to that point. So trig integrals, this is if you see powers of sines, powers of cosines, powers of secants or tangents, or multiplication of sine and cosine of different frequencies. And our main tricks here were Pythagorean identities into substitution or reduction formulas. For trig substitution, you're looking for square roots or weird powers of things like a squared minus x squared, a squared plus x squared, or x squared minus a squared. That's really the setup you're looking for to do a trig sub type problem. And then our process here was pick the right trig function, plug it in, solve the integral, which might involve trig integrals, and then convert things back to x. And our most recent method we talked about was partial fractions. And partial fractions show up when you have a rational function you're trying to integrate. And we have our standard method for solving these. Find the form of the decomposition, find the coefficients, and then integrate each term to find the antiderivative. These methods all show up in very specific types of situations, and they have a certain method to be followed when you try to solve them. That's why they all fall into the same sort of special techniques category, because when they show up, you know they're there and you know how to solve the problem from that point forward. So the example I want to look at is this one here. Compute the integral of 9 minus 4x squared over x dx. And the point you should see here is since I see a 9 minus 4x squared, this means I should be thinking trig sub. So first I'll rewrite the integrand a little bit, which since I now see a 9 minus stuff squared, means I should set my substitution to be 2x is 3 sine of theta. So then dx is going to be 3 halves cosine theta d theta after I divide through by 2. And then I can plug in the substitution. I'll get the integral square root of 9 minus 9 sine squared theta divided by a 3 halves sine theta times a cosine theta d theta with a 3 halves here as well. This 3 halves and this 3 halves cancel, and that part inside becomes a 3 cosine theta. So I then get 3 cosine theta times cosine theta over sine theta d theta. And so since cosine over sine is cotangent, I'm going to rewrite this a little bit as the integral of 3 cosine theta cotangent theta d theta. And this is a product, so we're going to go proceed here by integration by parts. So you could also at this point write this a little differently and go with trig integrals. But since this is what I saw, I'm going to do integration by parts. And the key thing here is, if you do it right, you should get the same answer no matter which way you solve this problem. So let's do integration by parts. I'm going to differentiate the cotangent term because I know how that works easily, and I'll integrate the cosine term. So I'll set u to be cotangent theta, then du is negative cosecant squared theta, d theta. I'll then set my dv to be cosine theta d theta, so my v is then sine theta. If I do that, I will get the following. This is a 3 out front times uv, cotangent theta sine theta, minus v du, sine theta times negative cosecant squared theta d theta. The minus signs here cancel. Cotangent is cosine over sine, so that'll cancel with one of the signs to give me here a 3 cosine theta. And then plus the sine cancels one of the cosecants to give me the integral of cosecant theta d theta. But that has a formula that looks exactly like the one we have for secant. So what I get here, so the trick here is if you multiply this by cosecant theta plus cotangent theta over cosecant theta plus cotangent theta, it becomes a negative 1 over u du. In the same way the secant one works when you multiply by secant plus tangent over secant plus tangent. So I will get a 3 cosine theta minus a log of cosecant theta cosecant theta plus cotangent theta plus c. And I have to convert this back to x. My original substitution was that 2x was 3 sine theta. So sine theta is 2x over 3. So 2x over 3. This then becomes root 9 minus 4x squared, as it should. And I can write out all of my expressions here. So 3 cosine theta becomes 3 times root 9 minus 4x squared over 3 minus log of cosecant, which is hypotenuse over opposite, plus cotangent, which is adjacent over opposite, plus c, and simplifying it out, root 9 minus 4x squared minus log of 3 plus root 9 minus 4x squared all over 2x. So now when you can see how these techniques sort of get themselves combined, right? Trig substitution gives us the way to start the problem, but then we might need trig integrals or integration by parts to solve it out from there, or a substitution even, a different substitution. All these methods can all work together, and they have their own place in how you solve these problems. So it's important to have a good grasp of all these methods, so when you see an integral, you can know, here's how I'm supposed to start this problem, and then you can do the first couple steps and see what it gives you. And if it gives you something that's easy, do it. If not, how do you solve that new problem? Ideally, the new problem is easier than the one you started with, but that'll give you a way to attack pretty much any problem you see that involves an integral. You have all these methods at your fingertips, pick which one you use to start based on its special technique or it's an easy setup you can see, and you'll find yourself well equipped to deal with pretty much any integration problem you might come across your studies.